lights over here, I got a detector right here. They hit at the same time, because I'm smack dab in the middle. If they hit at the same time, it'll glow red. If that one hits first, it'll glow green. They travel at the same speed, the same distance. It glows green.
Is it because you're like literally in the middle, and like maybe I'm not in the middle, so it would be different?
No, that's not the bit.
Does it matter about afterwards? Let's get there.
You said afterwards?
Yeah.
No, it's not an afterwards thing. How could that light get to here first if it travels the same distance and the same speed?
Is it acceleration then?
Assume we're not worried about acceleration.
Wait, are you at rest?
Yeah, I'm at rest relative to the detector. We're both at rest relative to whatever's going to flash the light.
So you're not moving relative to any other thing?
Right. We're all at rest. Except for the light that obviously has to travel.
Do they flash at the same, they flash at the same time, right?
That's what Ryan said.
But if one gets those two, it would, the only thing I can think of is one flashes before the other.
That is the secret. They do flash at the same time from Ryan's point of view. They do not flash at the same time from Peggy's point of view.
Yeah, that's what I was trying to say, like, when you're in the middle.
Okay. Just because two things happen simultaneously to one reference frame, it does not happen simultaneously to the other reference frame. That is the key. Because we think about these two things go off at once, immediately most people think, well, it goes off at the same time. I kept saying that's what Ryan said. And Peggy's conclusion was said, when I worded that one, I said, if they go off at the same time. But they don't go off at the same time from Peggy's point of view. The one on the right goes off first, and then the one on the left. This is the idea of simultaneity. Things are not necessarily happening at the same time. Now, let me exclude what this is not covering. If there's a lightning strike a mile away, we'll hear the thunder in about a fifth of a second. Someone who's another mile down the road will hear the thunder a fifth of a second after I do. The event, though, the lightning strike, still happened at the same time to both of us. We're not covering that, the fact that we don't sense it before the other person senses it. This is physically, the lights do not go off at the same time from Peggy's point of view, but they do go off at the same time from Ryan's point of view.
So what actually happens?
What actually happens?
Yeah, do they go off at the same time?
From his point of view, but from her point of view, they don't. The right one goes off first.
How are they both happening?
Pardon?
How are they both happening at the same time?
Are they both?
Happening at the same time, like, I don't,
I can't seem to visualize.
yeah.
All right.
How is, in one scenario, they're flashing at the same time, and the other scenario, one's flashing before the other?
Because light is the same speed, regardless of the reference frame. It all goes back to that one assumption right there. All right, to get into the math of it, I mean, besides saying that they don't go off at the same time, to me, the math is sort of the backbone of all of this, which means it's time for a derivation, which I know excites you to no ends. The derivation is just absolutely wonderful. This is actually crucial. It's called we're going to derive the Lorentz transformations. What is the relationship between position and time in the two? We've already talked about the difference in time dilation, but we need to talk about the difference in time events. So let's sort of get some background in. We will not finish the derivation today. but we can get close. Or- And that part should be hard. So when you're setting something up like this, setting some relativity problems up, you generally put it in terms of reference frames. I got S and S prime are my two frames here. And that's really not a whole lot better. And usually one of them is traveling at some speed relative to the other one. So this would be traveling at some speed u. And so this would be like you're in a car, car's cruising down the road at 50 miles per hour relative to the earth. You're in the back seat, and you throw something up to the front seat, whatever you're throwing, generally you can figure out how fast it's going relative to you. So this would be, say, the earth and the car. Eventually we'll throw in another object here, such as, you're in a car and you throw something. But we have two reference frames. The prime frame moves relative to what we're gonna, to this frame. They might both be moving relative to something else. All right. The other, so that is just common language that I'll be using to get me. The other thing we need to talk about is invariance. So the speed of light is the same, no matter what your reference frame is. Light's coming at you, you pull out your detector, it hits at a certain speed. You now travel half the speed of light, light's coming at you, you detect it, it's the exact same speed as if you weren't moving at all, whatever not moving means. So, but time's not the same. Length is not the same. Events happening at the same time is not the same. Is there anything else that is the same no matter what reference frame you're in? And the answer is yes. Let's go back to our box and mirror routine. Traveling some speed v. That distance there is h. And then in another reference frame, we'll just have a different speed. Just call this v prime. This distance here is h. So h is the same in both scenarios. Now, h is some value, so we can do better than that. If I look at my two triangles there, this is h, this is 1/2 vt, and that's the square root of L squared plus 1/2 vt. Try that again, h squared plus 1/2 vt squared. And in the other scenario, it's the same thing, except, well, that's still h, and this becomes the square root of h squared plus 1/2 v prime t prime squared. Time's not the same, so it's I'm just using prime to differentiate the two. Neither are proper. C is equal to distance over time, so in the top case, that is going to be, how do I want to do that? Two square root of h squared plus, instead of writing 1/2 vt, I'm just going to put in, I'm just going to call it x. X or 1/2 x, that's what it's put in my head right now. X is what I did. Over whatever time that is, and that should be equal to 2 times the square root of h squared plus x prime squared over t prime. twos cancel out, multiply both sides by t, and so I get t times the square root of, t prime times the square root of h squared plus x squared. That's not, sorry. Yeah, I just did this yesterday. All right, so ct is equal to the square root of h squared plus x squared. Ct prime is equal to the square root of h squared plus x prime squared. There we go. So just multiply both sides by t, multiply both sides by t prime. Square both sides, get rid of my radical, so I have c squared t squared is equal to h squared plus x squared. And then c squared t prime squared is equal to h squared plus x prime squared. Solve for h squared in both cases. And so h squared is equal to, in the first case, c squared t squared minus x squared, which equals, in the second case, c squared t prime squared minus x prime squared. So we have this relationship right here, which is also invariant. Yep, this is where I have it right there. So the other thing that is invariant is not only the speed of light, but c squared times whatever the time squared in your reference frame is minus the position squared. So we have a way of relating position and time between these two frames. If we're being really pedantic, properly, c squared delta t squared minus delta x squared. It would probably make sense at this point, given the time. We'll derive it next week. Now, the good news is, when I first was deriving E equals mc squared, which is ultimately where we're heading on this. When I first derived E equals mc squared, that was a 3-hour derivation. It's not that long anymore. I found a better derivation, takes much less time. So it's not 3 hours. I break it up into parts to make it seem like it's just a bunch of little steps. But it is heavily math derived. So just something to look forward to. When you're thinking, I haven't had enough math this week. It's gone.
Do we need to remember the derivation?
No, I'm not doing it for regurgitation purposes. I'm doing it so that you can see where the stuff comes from. The big difference between engineering and physics in my mind. Unless you get to the theoretical engineering stuff.
Suppose that same experiment with Peggy and Ryan,
Yeah.
right? So you said that the right goes off first, right light goes off first?
The
Oh.
right one gets there first.
Because
They
it
go
goes
off first.
off first.
The right one goes off first.
So what if, like, Peggy pressed them at the same time? Like, will the right one go off first?
So Ryan kicks him off at the same time?
No, Peggy.
If Peggy kicks him off at the same time, then they will not arrive at the same time to Ryan.
Oh.
So we just
That's
flip.
What if Peggy and Ryan switch positions?
Well,
Then they change their points of view. It is not person specific. Peggy just drew the short straw.
so is Ryan's assumption correct? That
That-
because the cart is moving, that's why?
Ryan's assumption, they went off at the same time in Ryan's reference frame.
Yeah.
So Ryan was correct because it was set up for them to go off at the same time in Ryan's reference frame.
Yeah, okay.
And if they had gone off at the same time from Peggy's reference frame, then they would have hit the detector at the exact same time, and it would have glowed red. It's just that they didn't go off at the same time, from Peggy's point of view. And a lesson to all of this, the faster you go, the less you age. So if you were speeding home, your watch is just gonna be a little bit off. Something to keep in mind. See you Thursday. Take some more time?
No, I'm like,
Okay. And Francis, you're good to go? All right.
You have a good night.
You too.